Okay, so it is now the noon hour. I burnt my finger in lab today, so if you see me putting my finger in ice, it's not the newest teaching craze, it's because it hurts. But this is where we left off, and I'm sure everyone knows that Hurricane Olivia is coming our way. I have no news about class on Wednesday. We'll just figure it out as it comes. They canceled most clubs for tomorrow, so if you have any extracurricular activities, they're likely canceled for tomorrow. Just if you don't look at your Maui announce, that'll all be on your Maui announce for the in your email. Anyways, so this is where we left off, and we're still looking at moles, looking at how moles, kind of things we can do from stoichiometry. That's chemical accounting. Okay, so for instance, starting with 1 gallon of water, so 1 gallon, and we should go from the left all the way to the right and end up with grams hydrogen. So one nice thing about dimensional analysis, if you get your units right, you can see everything cancel. So 1 gallon, so how do we convert? We're eventually going to go to grams, and we can get that. First of all, gallon's not a very useful unit, at least metric system, but there are 3.8 liters in a gallon, and if you ever, it's 3.78 actually, but if you look at, I guess we have 3 sig figs, I should put 3.78. If you ever look at a gallon of milk, they'll say 3.8 or 3.78. And that type of information will be given to you. I know it just because. But then, so density of water, well, I could go right to a kilogram, but I'll follow the units they give you here. So 1,000 milliliters per liter, and a liter of water weighs 1 kilogram. Milliliter of water, cubic centimeter of water, all the same thing, 1 gram of water. So gram per milliliter, and next thing we have to look at is, so we have a mole of water to 18 grams of water. It's just water. And then we have 2 moles hydrogen per, actually no, it's 1 mole, sorry. Hydrogen, H2O, 2 grams hydrogen per mole hydrogen. So the step here that might be kind of new is looking at here, the mole of hydrogen per mole of water. So because it's H2O, there is 1 part H2 and the whole part H2O. So there's another way you could do this, and this is equally acceptable. You could do 2 moles H and then do like 1 gram H. That's fine too. So there's 2 ways to solve the problem. Either way, and you put it in your calculator. Oh, and by the way, to those in class, we have Shane visiting us in the back. He is evaluating me, so I will try to be on my best behavior, as always. He's our STEM counselor, so if you ever have any questions, you need to see an academic counselor, it's Shane in the back. We might have Professor Emsley come too, so we'll see if she makes it. And putting this in your calculator, you get 420 grams. And so, and that's not that much. That's not even a pound, right? So that's about a pound, but a whole gallon of water, you get less than a pound of hydrogen out of it. And why is that? Well, because water is only 1/9 hydrogen by mass. So you can see the H2, the 2 hydrogen atoms, even though there's by atoms, water is mostly hydrogen, but by mass, it is 8 9 hydrogen, 1 9. I'm sorry, 8 9 oxygen, 1 9 hydrogen. So, how do we answer our questions with this? All right. Moving on, obtaining the empirical formula from data. And again, we're kind of going through some history here. Chemistry used to be, what is this stuff made of? And so we're following the same order since Linus Pauling literally wrote the book in 1960. And almost every chemistry class goes through this stuff. So it's not the fun stuff we do in chemistry yet, not the stuff with the gadgets and the CSI stuff. We'll get there eventually. But so what's an empirical formula? It's the lowest ratio of atoms. And one of the things to note, though, like these molecules up here, so C6H6, that's benzene. Okay, benzene, it's a liquid at room temperature. It smells very strongly. Not quite like gasoline, but kind of like gasoline. It's aromatic. And then C2H2, that's acetylene, or ethine is the proper name. Stuff they use in welding torches. Okay, so we have liquid benzene, and we have just kind of like gasoline. Then we have a gas that we use for welding, and they have the same ratio of atoms. But are they the same molecule? No. We talked about some molecules last class. So like fructose and glucose, those have the same formula, but they're both very different biologically, at least. They're similar, but not the same. Fructose tastes better than glucose. Okay, so how do we do this problem? And the compound contains nitrogen and oxygen. It produces 24 grams nitrogen and 70 grams oxygen. What is the empirical formula? So hopefully at this point in time you're thinking, okay, I'm given a mass of something, I should convert that to moles. So 24.5 grams of nitrogen, 70 grams of oxygen, and then mole nitrogen to 14 grams nitrogen, mole oxygen to 16 grams oxygen. And if you don't remember, I am getting those numbers right here on the bottom of the periodic table. So I know it's hard to see in the back, but under nitrogen is 14.007. I'm just saying 14. Oxygen is 15.9996, which I put as 16. Okay, so then we put this in our calculators. So 24.5 divided by 14, we get 1.75. 1.75, and then 70 divided by 16. And we get 4.375. And you're like, okay, great. So that means that we have nitrogen 1.75 and then oxygen 4.375. And this is, of course, is wrong, right? Because you can't do that because chemistry deals with discrete mathematics, whole numbers only. So, right, have you ever seen the things where you say like, oh, the average household has 2.5 kids or something like that? You know, what does a half a kid look like? People are only whole people. So you can only have 3 children or 2 children. You can't have 2.5. So what do? We divide then by the lowest. We divide both sides by 1.75. So dividing, of course, 1.75 by that 1.75 is 1.75. But doing the other one, now we have nitrogen 1, oxygen 2.5. This is still wrong. So what we have to do is we have to multiply by 2 to get rid of the fraction. And we have N2O5. And then this is our final answer for that. So the question I often get is, how do we know what to multiply by? And look at the fractions. If you get a half as a 0.5, multiply by 2. If you have an answer times that's 0.33, close to that, multiply by 3, that's about a third. If the answer is 0.25, multiply by 4 to get rid of that. And if it's 0.2, multiply it by 5. So that's the the fractions there, and so on. I mean, if it's something else, try 1/6 or 1/7. It's a weird answer. All right, so recap with this one. We're given data. We're given mass of elements. How do we try to figure out the ratio between the elements in a compound? First thing to do, convert the mass to moles. And once you do the moles, then you get the ratios where you get whole numbers. So remember, discrete mathematics, always use whole numbers and then work out to get whole numbers. In this case, we get the ratio of 1.75 moles of nitrogen to 4.375 moles of oxygen. Divide by the lowest number, 1.75, we get 1 mole of nitrogen to 2.5 moles of oxygen. To get rid of the half fraction, we multiply it by 2. Then get to N2O5. So questions with this? How to do this?
Discrete numbers?
Discrete mathematics. So continuous mathematics, like if you've seen y equals x squared and you get a parabola, right? And there's a difference between 1.002 and 1.003. There's an infinite number of data points between there, right? Whereas chemistry and everything else in the real world, you cannot. So space is also quantized. So go from point A to point B. There is not an infinite number of points between here because it takes time to go across space-time. There's an infinite amount of space you would never get from here to there. So same thing with atoms. There's small packets of existence. Other questions? Okay. Now your turn. Ibuprofen. Ibuprofen is 75.69% carbon, 8.8% hydrogen, 15.51% oxygen. So the last one I gave you mass, this one I give you percents. What do? You pick a number. 100. 100 is an easy number. So then you get 75.69 grams of carbon, 8.8 grams of hydrogen, 15.51 grams of oxygen. And then kind of go from there. This one I'm going to go around and see if you're following. So go ahead. I know I didn't put the answers up in the chem quiz, but I want to see how people are following. You probably don't. You don't have the periodic table memorized yet. You don't have to memorize it, don't worry, ever. So that'll be a good start. Is anyone completely lost and stuck? Raise your hand.
Not yet.
Looks like everyone is on his or her way. If you remembered from early in the notes, you're even given the answer. But I was going around and it looked like people were following, and divide by the lowest to get the ratio of 6.5 to 9 to 1, and multiply by 2. I know this is 18.15, but that's just an example of experimental error. So, and it's probably also a little truncation error because hydrogen is 1.008 grams per mole, and I had the 1 gram per mole here. So there would be a little bit of, so I guess go to 008 if you wanted to. But actually 8.088. That would probably give you a little better answer, but it's also truncation. Anyways, how are we doing? Questions so far on how to do this? Everyone's got it? Okay, good. And I know we're jumping around topics quite a bit in the beginning. And we're going to talk about how to balance chemical equations. So chemical equation is a bit like a recipe. So like when you make pancakes from scratch, right? Well, I guess the simplest way is to take the pre-made pancake mix, but if you make them from scratch, you take a cup of flour, an egg, 3/4 cup of milk or water, a teaspoon of baking powder. You blend it together and you heat it up and you get pancakes, right? So that's a recipe. The ingredients. So here's your recipe. We have 1 part CH4 methane plus 2 parts O2 oxygen reacts and form 1 part CO2 plus 2 parts water. And we haven't quite gotten to talk about the structures of things, but eventually CH4 is a tetrahedral structure. We'll get there in chapters 9 and 10. And oxygen here, diatomic molecule, is just two atoms, form linear CO2 and two kind of Mickey Mouse bent-looking waters. So what does CH4 mean? CH4 means there's one atom of carbon. Carbon is denoted here as the black sphere. And there are 1, 2, 3, 4 atoms of hydrogen. Oxygen, there are 2 atoms of oxygen, and there are 2 of them. So here there are 1, 2, 3, 4 atoms of oxygen. And one thing to note, when you balance chemical equations, there has to be the same number on both sides. So over here, there's 1 atom carbon. There's 1 atom carbon here. Oxygen's 1, 2, 3, 4. On this side, 1, 2, 3, 4. So 4 atoms on both sides. Same thing with the hydrogens. 1, 2, 3, 4 atoms of hydrogen here. And 1, 2, 3, 4 atoms of hydrogen there. So atoms in equal the atoms out, at least for chemical reactions. For nuclear reactions, you can change the identity of elements. But the same number and type of each element are the same on both sides of a balanced chemical equation. If they're not, then it's incorrect. The other thing is, when you balance a chemical equation, you can't change the molecules either. So let's say, for instance, I was balancing this equation, something like O2 plus H2 forms H2O. And like, you know what? I'm just going to put another 2 there. So now I'm balanced. The thing is, I mean, that is a correct balance equation, but H2O2, that's hydrogen peroxide. That's very different than water. So to balance water, it has to be that. I mean, I'll go over the logic in a second, but so to balance this, you pick an atom. This is a very simple one. You pick an atom. I'm going to pick oxygen, and here on the left side of the equation, there are 2 oxygens, and H2O, how do I get 2 oxygens there? I have to put a 2 in front of it, because not denoted there, that's really a 1. So 2 times 1 is 2. And if there are 4 hydrogens on the right, there have to be 4 hydrogens on the left for the 2 there. So let's follow the logic for another example here. Combustion of butane. So C4H10 butane plus oxygen makes carbon dioxide and water. So pick any element. I'm going to pick carbon. So 4 carbons on the left. So then 4 CO2s on the right. So now we have the right number of carbons. 10 hydrogens on the left. So 5 waters on the right. So you can probably see there's already starting to be a problem because we're going to have an even or an odd number of oxygens. So we have to have an even. So there's 2 ways you can do this. You can go ahead right now and multiply it by 2. So I can just do 2 and just already put 8 and 10. The other thing I can do is I can balance it to get some number here in front of the oxygen, and a fraction, and then just multiply the terms with the fraction. I'll do that. I'll start this way, and I'll show you the other way to do it. Okay, so doing it this way, we have 8 CO2s, and 10 waters. So here we're going to have 16 oxygens. I'm going to do OX for oxygen. And here we have 10 oxygens. So I'm just putting OX because my O's look like zeros because I don't really do any difference. So this 8 times 2 is where we get the 16 from, and 10 times 1 for that. So this is going to form 8 oxygens, 8 O2s, and this is going to be 5 O2s. So the answer here is 13. So I can up there denote it as a halves, or I can do 16 plus 10, that's 26, and then 2 O2s, 26 divided by 2 is 13. I can do it that way. I mentioned I could do a fractional way of doing it. Let me do it this way. And these all give you the same answer. I hope I'm not confusing you by showing you multiple ways. So 4 and 5. If I wanted to balance this then, let's see here, that would be 9. This would be 9 halves oxygen. So, is that right? No, that's not right. Actually, it would be 13 halves. What am I doing? Yeah, because 4 times 2 is 8 plus 5 is 13. So that's 13 halves or 6.5, however you want to put it. And then you can multiply it by 2. Then you can just multiply the whole thing by 2 and then get the 2. 2, 8, and 10. So, sorry that I'm giving you multiple ways of doing it. I just wanted to, because there are multiple ways to do it. But procedure is pick an atom, balance the equation with atom, pick another atom, balance it with that, pick a third one, and keep on going until you have whole numbers only of all the molecules and or atoms. Because you can have like an elemental, just like iron, metal, or something like that. So, questions on how to do this? All right, let's see if you can do this. How many waters are in the balanced chemical equation here? So C6H13 burning an oxygen to form carbon dioxide and water. What is the number of waters in this balanced chemical reaction? Chemical equation. And which answer do we know is absolutely wrong?
A.
A. Why? Yeah. Yep. Decimal fraction. Can't be A. Is anyone stuck? Raise your hand if you're getting stuck. So feel free to talk to your neighbors. Need help? A little lost? Okay, where are you stuck? Okay, so one carbon, and then H4, so you need to have an H2O, so you need 2 waters, so it's not 2 of the 4 hydrogens. Yeah, and now you gotta look at the oxygens. There are 2 oxygens here and 2 oxygens there, so there's 4. There's 4 O atoms, so you have 4 O atoms on the left. Yeah, the subscript, so you were here, I don't know if you've been watching. The subscript means number of. Yeah, okay. And you would be confused.
Okay, so in this one we've got 6 carbon here.
And you have 6. Yeah.
So we need to what we're looking at.
Well, water.
Okay. So exclusively looking at H's and O's here. I'm not looking at this one.
Well, you have to balance the whole thing. You have to get everything balanced to look at it.
So which one of these numbers is going in there?
Okay, that's just the answer.
Okay.
That's multiple choice, right?
Okay. So the answer to here.
It's the answer to that.
Okay. Alright.
But you can't really look at that and come up with the answer, except for A is wrong. And A is wrong.
Yeah. So that's 13. Then I need to make this.
Well, with the 13 there, you know you're going to have to multiply by 2 at least once.
So let's go in that case. I need to look at those 2 numbers.
You have to balance the whole thing. Okay, so what I would do, I would start with the carbons. And there's 6 here, so I put a 6 there. Okay, now, when if you look at the hydrogens, there's an odd number. I would multiply this by 2, and then this becomes 12. And now you would need 13 waters. Yeah, but then now you have another odd number, so you have to multiply by 2 again. So that would be 4. 24 and 26. And then now you can 13 plus 24 would be
37.
So this is 37. Okay, so I'm doing half of this. And where's the 4 coming from?
4 for what?
So
Okay, so O2, there's 2 oxygen atoms. Okay, we can look at it that way. So if you look at the number of oxygen atoms on the right here, there's 24 times 2 is 48 plus 26. So 48 plus 26, that's going to be 70. That's going to be 72. And then, no, wait.
it's on your phone.
No, okay, 48 plus 26, 74, sorry, and then you're going to do that and divide it by 2.
I'm not saying anything. Okay. All right. Thank you.
Yeah, are you following?
Yeah, slowly.
Okay. Good. Okay. Yeah. Okay, good. That's not confused. Happy smile. Okay. Hopefully we'll see that smile through the whole semester. Your dad.
It's just space, or is it not? Okay, I'm like, why am I looking at this and it doesn't make sense now?
So you have 13 hydrogens here and 2 here. So already you know like 2. So there are 2 times 6 is 12 carbons here. So you have to put 12 carbons there. And then 13 water because that's 26 and 2 times 13 is 26 and 2 times 13 is 26. Okay, so
I get to choose here, so you can't choose those conflicts. We here to choose here, so we have to choose
Question
one.
is, how many?
So 2 times 13 is
So we just got to count how many we have here.
To have it balance. To balance that equation is going to result in how many we have.
So 2,
And it's going to be
this is
the
twelve,
13,
2, each 15,
So we just have to count.
26.
so that would be 26.
It gets tricky, but this 12 times 2 is 24.
So what happens is 24.
So this is what I get confused. So I have to make one
I
eight.
don't know if that makes it's weird. It's always easier.
I have to make this one.
I don't know.
Right now the coefficient is 1.
Yeah.
So
this-
the question is, you do that one or that one. So if you do 24, or 24,
Like here.
yeah, just for,
Start there.
so that would mean 24 times 2 hydrogens,
If they have 48.
But it seems to me like since
Yeah,
we're just
48.
and that'd be 24
but
of those.
everything I've been looking at, there's CO2
Yeah. And now, this side of the equation has how many O's overall.
This side or this side?
This side.
So this should be
So as long as we want
12,
to things with
4, so 4, 6, 7, 6.
Okay, then
So this is basically
so large because it's going to
yeah.
change.
And one is
Alright, so now I'm writing for that and try to zero.
I have to make the same thing here.
Yeah. So now we see what's our carbon.
So this is 13.
No, it's not carbon. So we have 6, yeah, so we automatically know we can put 6 in front of that.
I'm
And then
gonna
that
run
changes
them
the whole equation.
that's
So
what
this would be
6
6.
C's,
So it would be 6 here too.
and then the O2 is just 1, and others are 12.
So this is
Add that.
okay, so this number is 8 is equal to 8, so 38.
Yeah.
But Isn't it?
This is
So 13 and then so I'll do 13 too.
no.
Wow.
Alright, we have 13 on this side. How many H's on that side?
And this is 24.
No, we have 48.
Oh, 48.
So, how do we get that to 48?
So we have to out. Oh, we have to out.
And it's
And
obviously,
13 then.
yeah, so you have to go the next one up and really go first. This is like a short-term memory thing. And I'm saying that in mind.
All you
Pretty clean.
Okay, now I don't understand.
Okay, just look at one. It's just down. So we'll start with C's. 24 C's. 12, 50. 52 H's. 37, 32. 24 O's. Okay. 24 C's.
Yeah, it's better than
48 O's. Okay, 48. 74, 44, 26 times 2 is 52. And
So how many?
so we can reduce this. That's odd numbers, but we can't. If that was a 36, you can take out 4. But since it's not, it's what it is. Because you want to reduce it as much as possible. Simplify it. But it can't be simplified. So you can still do that.
Okay, so. So we have 48. So we have to make the 48. So you have to multiply something 6 by something have to give me 48, yeah?
What is what's the one you want to balance?
So I'm going to start with C. So we have 48. And here we have 6.
You're doing carbon?
Yes.
Right now,
Oh, we did fraction because we have the 6 here.
yeah.
But do we have to say that?
So start with 1, and then you move on to the next one.
Okay, so today we can do 1. So we're going to share.
H is balanced.
My age is not.
Make them balanced.
Okay, so we have 48.
Yeah, that's where we were.
Yeah, we were here.
So, okay, so 13 doesn't go on 48, but it has to go on the next one. What is 13 and 48 both go into higher?
Oh, yeah.
No, it just has to be above it.
48 is bigger than 48?
Yeah.
It will be 50, so 52?
Yeah.
It's not
52 times 15,
Divided by 6.
So we put the, so in this case we put the 52 here.
No.
So what do we do with the 52?
Maybe you just start over.
I didn't read that.
No, erase this. Just change the page. Okay, C6. H 13.
I got it in the
All right.
I got it here.
So
Now it's getting complicated here.
everyone has converged. The answer is, of course, C. So we are going to kind of change topics. We're going to move on to something else. And we're in chapter 4 now. And let me propose a question to you. Does your car run on air or fuel? What do you think? Air, yeah. If you think about it, actually your car runs more on air than fuel. Of course it runs on fuel, but if you look at this equation here, I have octane here, C8H18. That is octane. And octane there reacts with oxygen to form carbon dioxide and water. And where we've gone right now, this is the balanced chemical equation. 2 octanes plus 25 oxygens make 16 carbon dioxides and 18 waters. So octane, it's 114 grams per mole. So if you get the 12 times 8 plus 1 times 18 gets you 114 grams per mole. Oxygen, 16 times 2, 32 grams per mole. Carbon dioxide, 12 plus 16 times 2, 44. Water, 2 plus 16, 18 grams per mole. And 2 octanes is 228 grams. 32 times 25 is 800 grams. So on the left side of the equation, we have 1,028 grams of reactants. And then carbon dioxide and water. So 16 times 44 is 704 grams. 18 times 18 is 342. Those added together are 1,028. So we have 1,028 grams on the left, 1,028 grams on the right. We have the same number of each type of atom. So this is the conservation of mass, right? So what? Why do we care? I was a consultant for a billionaire named Robert Addington. And this is when carbon credits were kind of the fad. We're like, okay, we're going to start. Have you heard of carbon credits before, or carbon tax? It was proposed that we would have a carbon tax of $30 per ton of CO2. And then you could get certain number of carbon credits. If you had certain things you could do, you could get more carbon credits, you could sell them, and you were also allowed to pollute so much CO2, if you even call it pollution of sorts. He was wondering, and he was mostly coal, he was wondering why there was so many carbon credits in coal. Well, 12 grams of carbon, which is coal is mostly carbon, reacts with oxygen to form 44 grams of CO2. So you have a huge mass increase when you burn something. So, right, we have 200 grams of fuel making a kilogram of product, thereabouts. So we're increasing its mass by a factor of about 5. So just by adding oxygen to it. And then it was interesting, well, we don't have carbon credits now, but I remember Robert Addington, he was really excited. He's like, I really want carbon credits. This is a great thing. Because he goes, well, we can buy some mineral rights to land. We can strip mine the land. That's common in Appalachia. You can just, take off the top layers of soil and get the coal seams, grab the coal seams, and then they have to remediate the land anyways, plant trees. And he goes, oh, I could have like 1,000. I could have like a million acres of land. I could strip mine. The coal could be worth 100 million. So I know that the dollar should be first. And then, so if I had a million acres of land, I could sell the coal for 100 million. Then I could plant trees, and trees produce 20 ton. They could sequester 20 tons of CO2. So per acre per year. So that means that the million acres would have 20 million tons of CO2 per acre per year, and at $30 per ton, I would make $600 million per year from my coal fields that I'm just remediating that I have to do anyways. Like, this is a great thing. I want carbon credits. So, but we didn't do it. Of course, well, the United States, we don't have carbon credits. So, there was a whole bunch of research going on, and I mentioned the 20 tons per acre per year of forest. There were calculations, and researching to see what kind of crops, how much CO2 do they gather and do they sequester. And part of the problem is that we are doing the research in the United States of America, and if you know anything about the United States of America, we have some of the best cropland, most likely the best cropland in the world. So the Mississippi River Valley is just amazing soil. And the reason we had to thank that is because of Canada. Because every 100,000 years or so, all the topsoil gets scraped off of Canada by glaciation. It gets dumped right into Indiana, Ohio, and Iowa. So this is where the glaciers stop. So we got tons and tons of topsoil, just amazing topsoil in that area of the country. And if you grow anything in Ohio, Indiana, Illinois, Iowa, it's going to outperform anyone. And they were doing the same research in Ireland. Ireland was like, okay, we can get the carbon credit gain too, and like we can't match your crop yields, America. We're not even close. It's because our soil's better. Thanks, Canada. So that's kind of where we left the argument off because the laws didn't pass, so we stopped doing research on that. But what we did look at it was in algae. Algae was the next question is, what about algae? Algae is also a great option for biofuels and anything in general for yields. So if you look at corn, corn is what we have, or soybeans. Corn is what we get our biofuels here in the United States, and here in Hawaii. We don't grow it here, we import it, but we get a corn ethanol. For corn to grow, it has to put down roots, it has to grow a stalk, has to grow leaves, and it grows a fruit. And we get the ethanol comes from fermentation of the sugars in the fruit. But it has to do all this energy to grow the other stuff. Algae is just single-celled, divide. So get much more biomass, or whatever it is you're looking for much more, it's energy efficient. So it's time and energy efficient. So algae, we're looking at other drawbacks of algae. Yes, capital costs are the main thing. Capital costs are huge. I mean, to grow a field of corn, you just need to, it's minimal effort compared to algae. The proven method for algae is called the open pond method, where you have just like a kind of a lake, like if you want a shallow lake, and then you grow the algae there. So with that though, there's a lot of water loss, all that area, a lot of evaporation. So what can you do? You can put a sheet of plastic over it, and then it limits that. But that sheet of plastic, more capital, more money. So corn is still cheaper than algae. Another problem with algae is that about every 2 weeks, the whole colony dies. So, and the reason for that is because of invasive species. So when you get a crop of algae, the first couple of days, it does extremely well. And then about 2 weeks later, it all dies. And then, so you can replant it, but you have to keep on doing that. So the cycle goes through that way. Have you ever heard of the author, Weir is his last name? I think it's Andy Weir. He wrote The Martian. You ever seen that movie? Or no, you haven't. I like it. I like that writer. He wrote a book called Artemis. It has a moon colony, and all the, I don't know what to call them, astronauts, colonists, they ate food. They called it gunk. It was basically algae. So algae we're looking at as maybe a potential food source for colonists on the moon and or Mars, because of what I said, that you're not going to grow taro, you're not going to grow corn because it takes too long. You're going to grow single-celled algae because it's fast, and we can bioengineer algae to put out things like protein, like certain types of fats. So, and we do this now here in Hawaii for like omega-3 fatty acids. They use that in baby formula. There's a company in the Big Island that does that. They use a different type of algae. They don't use photosynthetic algae. They use the fermentation algae for that. So they get the nutrients from the bottom of the ocean. They grow that. That's on the Kona side of the Big Island. So they have a company that does that. So it's not necessarily photosynthetic. The stuff that we'd use for colonization would be photosynthetic algae. So, so we're looking at it. So we're looking at algae. We were looking at it not just for carbon credits. Well, Al Gore wanted to do this. So algae grows until it's limited by something. And if you look at the Mississippi River Valley, the limiting nutrient for the Mississippi River Valley is phosphorus. So if you add phosphorus to the waterways of the Mississippi River Valley, you'll get an algal bloom. And that's something it's a form of pollution called eutrophication. And we used to have phosphate in laundry detergent and in dishwasher liquid, so dishwasher stuff. And that's now banned. The thing with, because the United States of America, if you ban something in one state, it would be okay in, I'm not sure what the limiting reagent is here in Hawaii. It's either nitrogen or phosphorus probably. But here in Hawaii, our waters are actually extremely nutrient poor. We're not likely to have algal blooms because of our waters being nutrient poor. So, but if you look at the Pacific coast, Gulf of Mexico, those waters are much more nutrient rich. An easy way to tell if an ocean is nutrient poor or nutrient rich is that the ocean smells like fish. So if you ever go to like San Francisco Bay, the Oregon coast, and take a big breather of the air by the water, if it smells like fish, it's full of nutrients. If you go up to the beaches in Hawaii and take a deep breath, it's probably, if it smells bad, it could be nutrient rich, but it's from runoff, something, usually human runoff here, unfortunately. But so the nutrient-rich waters smell bad. Anyways, so and the waters in and around Alaska. So well, actually, I guess I back up to the waters in and around the Gulf of Mexico. Nitrogen is the limiting reagent, limiting nutrient, and in the spring runoffs, frequently coming from the United States, a lot of nitrogen fertilizers will wash down the Mississippi River in the Gulf of Mexico, and they'll get algal blooms, sometimes red algae. And those are from the extra nutrients of the eutrophication from the farm runoff. And eutrophication is not always bad. In Alaska, around there, the limiting nutrient is sulfur. And then the areas around Alaska, the ocean is actually very shallow there. And when the seasons change, the ocean currents change and churns up water stuff from the bottom of the ocean. Sulfur comes up, and there's a huge algal bloom around Alaska. And actually, the algae, that's where we get our oxygen from, here on Earth. So on the order of 75 to 80% of the oxygen on the Earth comes from algae. Doesn't come from trees, doesn't come from grass. So if we were like alien explorers and we were looking at the Earth, we'd say, okay, we have a planet that is mostly made of iron, that has a silicate crust with 2/3 covered in water, and the dominant species is single-celled algae because it changes the atmosphere and gives 80% of the oxygen in the atmosphere. And there's these little tiny two bipedal creatures that go around and think they own the place. Okay, so algae is really what rules the Earth. And well, the research was going towards the carbon credits because around Antarctica, iron is the limiting nutrient. So if you dump iron in Antarctica, there would be an algal bloom. Oh, and also connection back to Hawaii, the algal blooms around Alaska. Krill then eat the algae, and then we get our humpback whales come up, then they eat the krill that come from that, and then they come back down to Hawaii to mate and give birth, right? So they have those periods of weeks of binges and then the months of starvation. So all connecting, it's because of algae, and we have that relationship with them. Okay, so actually everything I talked about you've already learned, right? You've already learned, maybe not the chemistry and society kind of stuff, but all these things here, does your car run on air or fuel? You could go and have a conversation with someone about that, and you could argue carbon credits if you want. So you have those tool sets now. So think about that. So studying more chemistry. Anyways, let me go deep back into childhood. How do you make a Happy Meal? What is in a Happy Meal? What's that? No nutrition. Okay. How about things that I can buy that are empty calories? There are calories though. Okay, there's a toy. Oh, jeez. Sorry about that. I should just. My wife gets mad at me when I close Skype. So I should. Okay, Happy Meal. We have a toy. What else do we have? Fries.
Drink.
Drink. Anything else? I remember these. Of course, this was 30 years ago, but I remember like a burger. They still have them?
It's either chicken nuggets or
Okay, fine. Well, chicken nuggets.
something. I don't.
I'll call them chicken lumps.
Lumps.
There we go. We get some chicken lumps. All right. So, if I have 1,000 toys, if I have 10 fries, 1,000 drinks, and 20,000 chicken lumps, a lot of chicken lumps. How many Happy Meals can I make? 10. Why? I got 20,000 chicken lumps. Yeah, so I'm limited by something, right? So so say I'm working at McDonald's and I say, hey boss, I can't make any more Happy Meals. He goes, all right, I'll fix that. I'm gonna order 1,000,000 toys and I never want to hear you talk to me again about not being able to make Happy Meals. So yeah, this doesn't work because I'm still limited by the fries. So the fries here are what limit that. So if I wanted to make 1,000 Happy Meals, I would need 1,000 fries to do that. So this is nice because this is all 1 to 1 to 1 to 1. So here is my balanced ham sandwiches chemical equation. 2 slices of bread plus 1 slice of ham makes a ham sandwich. So if I have 1,000 pieces of bread and 1,000 pieces of ham, how many ham sandwiches can I make? 500. Why not 1,000? Because there's a 2 to 1 ratio, right? So there's a molar ratio, parts ratio, 2 parts bread to 1 part ham. So I would have 500 sandwiches plus I would have excess ham. I would have 500 slices of ham left over. So hopefully you can see where I'm getting at. I'm getting at the idea of a limiting reagent. So this concept is called limiting reagent, and chemical reactions are limited by something that it'll react until, if given enough time, mind you, sometimes if you stop a chemical reaction short, if you throw water on your fire will go out, not because it runs out of wood, because it took away the heat, kind of thing, right? You can stop chemical reactions not just by taking away the reactants, but given enough time, things will react until they are limited by something. And your car is actually a limiting reagent problem, but you don't worry about the oxygen running out. So in a car, you worry about the fuel running out because there's so much excess oxygen. Mind you, if you're in space, and there are some rockets that run off of fuel, the Saturn V rockets to the moon, those ran off of kerosene. So kerosene and oxygen, so they carried oxygen in the rockets with them. So if you ever seen Apollo 13, one of the things they kicked the oxygen tanks and then it ruptured, and that was a big deal, right? So you carry the oxygen with you in space if you want to react. If your thrust comes from a combustion reaction, actually, well, that's the only way that we know how to travel now is by thrust combustion. But all right, so the simplest problem with limiting reagent is excess of 1. So here's our carbon credits research. In photosynthesis, we convert carbon dioxide to water, or it's carbon dioxide and water into glucose and oxygen by the photosynthesis reaction. So 6 carbon dioxides plus 6 waters makes 6 oxygens and 1 molecule of glucose. We determined that a plant consumes 37.8 grams of carbon dioxide in 1 week, and so we have 37.8 grams of that. We have excess water. How much glucose can you make from the CO2? More likely, this experiment would have done the other way around. It's much easier to measure the glucose than how much carbon dioxide has been consumed, because you have to do it by pressure and whatnot and mass out all the CO2. So it's more likely that the amount of glucose from the algae, I'm assuming it's algae. Let's say aquatic plant. Yeah. So no, it just says it's in water. Okay. You're more likely to look at the amount of glucose that was formed. Even other than that, just the biomass, because plants make everything from CO2 and water. They and potassium. They have other things that they need too, but specifically phosphorus, potassium, and nitrogen. They need a lot of that. But they make everything, and they also other plant molecules are called alkaloids. So things like caffeine and nicotine. Nitrogen bases, those are known as alkaloids. They're all made by plants. But anyways, back to here. So let's do this problem here. CO2, we have 37.8 grams of CO2. So we're going to get to, we need to get to mass of glucose. So, so mole. So you should start thinking moles already in chemistry class. So carbon dioxide is 44 grams per mole. And here's the new step that we need to look at. So for every 6 parts CO2, so for every 6 moles of carbon dioxide, we make 1 mole of glucose. Glucose, GLU, is C6H12O6. And then, if you remember, we've done this, I have it memorized, but before, the molecular weight of glucose is 180 grams per mole. So the new step, you're probably familiar with all this dimension analysis. The new step you have to worry about is this 1 part glucose to 6 parts CO2. And you get that from the balanced chemical equation. So the chemical equation, of course, this is the other thing. It's important the equation is balanced, because if you have the wrong ratio, you get the wrong answer. So the balance has to have the right ratio to get the right conversion here. So there's the new step. And then the dimensional analysis here. So grams glucose cancel, moles CO2 cancel, moles glucose. And so whatever, 37.8 divided by 44 divided by 6 times 180, and then we get 25.8 grams. Does anybody want to see the calculator? Raise your hand. Okay. Okay, recap. So we have a living reagent problem that we have an excess of one reactant and then a limited quantity of another reactant. So we know that in this case, that the carbon dioxide is a limiting reagent. So we look at this one, and then by using the balanced chemical equation and dimensional analysis, so mass of a reactant, convert it to moles, use the balanced chemical equation to get the ratio of the product in moles, and then the molecular weight to go back to mass to get the amount of product that we'll get from that limited amount of reactant. So questions on how to do this? Okay. Now here's some pictures. So this is actually, for once the textbook gets this right, this is actually how we make ammonia. So ammonia is a very important molecule because it's where we get our fertilizer from. So so the primary plant nutrients are nitrogen, potassium, and phosphorus. Potassium and phosphorus we mine. Nitrogen we used to mine, but we were running out of it too quickly, and we generate it from air. So now we generate it from natural gas and air. We take natural gas, react it with steam called steam reformation to make hydrogen, and then we take air. Air is 78% nitrogen, and then we can react them, and actually it's over an iron catalyst. So if you react it over iron, you get ammonia. And I'm limited by time. I think we might even have class canceled on Wednesday, so I don't want to linger too much about this. I normally like to talk a little bit about why do we care about chemistry, why is it important? But this is important because this reaction actually allowed a population boom. So if you look at human population over time, around the year 1900, we were at a population of about 2 billion, and today we're like 8 billion, 7 billion, 8 billion. So something happened between 1900 and 2018 that our population went, and there's two things. So one of them is nitrogen synthesis, ammonia synthesis. Can anyone guess what the other one is? What? Medicine. Do you know specifically what? Yeah, not penicillin, but actually, not vaccine, but sulfa drugs. Antibiotic. Yeah, good guess though. Yeah, but started with sulfa drugs, yeah, penicillin. So antibiotics. That's the other thing, is because if you look at what the cause of death was before 1940s, so I guess about 1930s, it was infectious disease. People died from septicemia, tuberculosis, pneumonia. What do people die from now? Well, people our age die from accidents and murder and suicide. So that's the main cause of death for our age. But what about most of the population? What's the cause of death? So cardiovascular, so heart attack, stroke, and cancer. So that's what the old people diseases. I mean, not that we can't die from heart attack, stroke, or cancer, but it's unlikely for people in their 20s and 30s to be taken that way. So we had more people in the reproductive age, and then we had a bunch of food. Everyone could be fed, and we are all fed probably a little too well. Go to Krispy Kreme and get all the donuts you want, right? And how can you have those donuts? Because of ammonia synthesis. Because now we have the plant nutrients, and our crops are crops on steroids. So we have the United States of America, the best cropland in the world, and we jam-pack it full of nitrogen fertilizers. And like if you look, I told you the studies that looked at plants. If you put nitrogen fertilizers on plants, their roots are amazingly huge, and there's lots and lots of different roots. So it greatly improves the root system of plants with those nitrogen fertilizers. So they are steroidal corn that we're getting. Steroidal wheat, steroidal corn. We have tons of it. So lots of donuts for me to eat. And also a little bit of politics. So World War I. So Germany is the one that figured this out. So Germany, the BASF Corporation, that's like Dow Chemical is a big chemical company in the United States. BASF is huge in Germany. They figured this out. You can take ammonia, you can burn it to form nitrogen monoxide. You can take that, react with water to form nitric acid, HNO3. So maybe you've heard of explosives like nitroglycerin. How do you make nitroglycerin? You make nitric acid with glycerin. That makes nitroglycerin. Have you ever heard of TNT? Does anybody know what TNT stands for? Trinitrotoluene. How do you form trinitrotoluene? You take toluene, you mix it with nitric acid. So if you notice, that's why we don't have any nitric acid in the chem lab. We do have some, but we don't have it readily sitting out, because if you mix nitric acid with stuff, they tend to make explosives. And that is also why you cannot bring liquids on airplanes anymore. And that's when they scan, they look for nitrates. Because if you took glycerin and you took nitric acid, you took it together, you mixed it up, and you slammed it on the wall of the plane, you would blow up. It would blow up. Nitroglycerin is shock sensitive. So what's that? Yeah. So nitroglycerin is shock sensitive, but if you mix it with clay, diatomaceous earth, if you mix nitroglycerin with clay, and then you can get a very stable explosive called dynamite. Dynamite is nitroglycerin mixed with clay. And the person that figured that out was Alfred Nobel. So
when he figured it out, he did that because he owned a nitroglycerin plant, and it exploded. One of them exploded, and his brother died. So he's, I can make this a safer explosive. So he made a dynamite, and then they started calling him the Doctor of Death. So because it's a great explosive, it's good for making holes in mountains to put trains through, but it's also good for killing people. So Nobel felt really bad about this, and so he hired some people to think, like, how can I not be the Doctor of Death? And they said, you know what, so set aside some money, so when you die, you can have this fund, and this group of people will decide there's someone on this earth who is really dedicated towards peace, and then give that person a prize based off of a foundation that you form, and then you'll be known for peace and not as a Doctor of Death, and that's where we got the Nobel Peace Prize. And Nobel was Swedish. Nobel also, he loved this idea, so he liked science too. So we have Nobel Prizes in chemistry, physics, physiology, economics, and literature. Literature because he thought he was a good writer, but his family has tried to hide all his stories because he was really bad, apparently, writer. But those are the 5 Nobel Prizes offered through the King of Sweden in Sweden. The Nobel Peace Prize is offered through Norway. So Norway were the hippies of the 1920s and 1930s. So if they were like, okay, it's kind of like so if I wanted to find the peaceful place in the United States, where would I go? You think like Haight-Ashbury, Berkeley. That's probably, you think San Francisco. That's like our hippie, peaceful central United States. Norway was the hippie central in Europe back in that time. So that's why the Nobel Prize is offered through that. And also more politics. Well, Germany figured this out, and without this, they could not have fought World War I. So Germany invaded Prussia. So they did it after they had ammonia synthesis and could make explosives. Also, the iron catalyst, it wasn't until 1970 figured this out. It was Swedish iron ore. So Swedish iron ore, if you heat in the presence of hydrogen for about 8 hours, you can form a catalyst. How they figured that out, I have no idea. But that was Carl Bosch that figured that out. And because of that, though, if you know your history, World War II, Sweden was neutral. So, and what they struck a deal with Hitler. Hitler said, okay, I can either invade you, Sweden, or you can give me the iron ore that I need for the catalyst to make ammonia. So Sweden struck a deal that they were neutral, but they still provided the Third Reich with the iron ore they needed. So I don't know if it's more of a tribute than that. So a lot of politics and history in this thing. And also, like I said, all of our donuts that we can get. So, okay, we got 2 minutes left. I don't think I can get to there. Oh, I can. This limiting reagent here. Get a flask. So if we have this flask react, what's going to happen? Well, I can tell you the answer real fast because we're running out of time. These 2 nitrogens will make 4 ammonias, and then we'll have a little bit of excess hydrogen as denoted by the flask on the right, the C flask. A has not reacted completely. B is the right number of nitrogen, but there's excess hydrogen. That's not accounted for. But we will end here today, and hopefully see you Wednesday, and I can talk about limiting reagents that we can't tell. We don't have one excess. So, okay. I will hopefully see you Wednesday, if not the following Monday.
Mm.